All right, well, as Dr. Conrad mentioned, my name is Tyler Major. I'll be presenting was done in conjunction with Pranay and under the purview of Dr. Conrad and Dr. Weldon here. It's the simulation and measurement of an Internet of Things and IoT implementation of a digitally reprogrammable inductor. So a little bit of what we're going to go over today. We're going to go over what the whole Internet of Things schematic is. We're going to get over what the digitally reprogrammable inductor is. We'll show the simulations of both of these things, the design overview, the interface that we chose for it, the experiment we used to validate our results, and then some data analysis to look at the conclusions of what those were. All right, so a little bit about this. So first of all, we used a schematic called a discrete time non-Foster inductive circuit. Now, this is under the purview of discrete time systems. So if anyone has ever taken discrete time systems, and even more so if you have not, you know that the conventional schematic is you have an A to D converter, you have some sort of H processing that goes on into that, then you have a D to A converter and spit it back out. That's what's known as a Foster circuit. Now we have these things that are relatively new and being implemented called non-Foster circuits. We'll get into more of what those are. But first of all, why did we decide to do this research? What practical use can this be? I mean, it's all well and good. We have this thing that's a little bit novel. We did a little thing. Here's some graphs on it. What can be used for? Well, this has a lot of applications in impedance matching. Since we do have a digitally reprogrammable inductor effectively, what we can do now is, instead of people doing impedance matching circuits in an analog sense, building these, putting them on a circuit board, soldering them down, putting them in line with the system, now they could put our system in the middle of that, and if the system somehow changes, just with components changing over time, with heat, or they want to change their system up a little bit and they don't want to buy a whole nother circuit board or anything, they can just reprogram it, and since it's an Internet of Things schematic, they don't even have to jack into it and plug into it anymore. It can all be done over the network. Decided to do this because even though you can do this in an analog sense, making these in an analog fashion, as will be shown, is actually quite difficult, and the difficulty arises in the stability of that. And as I said before, since it's programmable and on the fly, they can just change it anytime that they want. So even though it doesn't follow the traditional 1 block, 2 block, 3 block schematic, an ADC, a DAC, and signal processing, so it still fits under the purview of what everyone would want. Also with this, we can have a negative inductance, which that will be shown, I thought, a little bit cool at least. So this schematic right here is what is known. All right, as you can tell, there's feedback into it. Specifically, what's to note about this feedback is that we're feeding current into the system, but what we're feeding back through our DAC is actually a voltage. So present on the, we have a tuned voltage feeding into an untuned current, what we're going to use. So how do we model this system now, since it's all in a continuous time sense has been done before, but we need to discretize the system now. So about how to do that. This time we have just voltage across the inductor, L dI over dt. We get the discrete time approximation. We do a little bit of massaging on the equations there. And at the bottom we get a discrete time model of what our voltage for the representative of the system is, including that R serial that you see there. That is induced by any sort of input impedance into the system. So before we go out and spend a whole bunch of money building this thing, what we want to find out are our constraints within the system. Figure in Circuit 1 and the Agilent Design Studio, the ADS system. So the parameters that we chose for this simulation was just a 20 millihenry inductor, 100 ohm, negative 100 ohm resistance there actually, and clock frequency, 50 ohm impedance, sampling time, all that sort of stuff. And then we have this long equation that is the entire system with the programmable. Now, within this, we wanted to make sure that this wasn't just a complete non-actualizable signal, that we wanted to make sure that it didn't only exist in ideal constraints. Second, delay time, just so we could simulate this being an actual system itself. So, the results of the simulation here. So as you can see, we have the red dashed line, which is the voltage into the system. And as we can see, but you can tell it's a positive inductance because the blue line, which is the current into the system, so that's key looking into the future. So thing to notice here, positive slope on our current whenever we have a positive voltage going into the system because we have a positive inductance. Now, moving over to the Internet of Things implementation. So what we have for this entire system is we have our digital non-Foster circuit, but within that we have an FRDM board. And connected to the FRDM board wirelessly is a laptop server that we're running. Now this laptop server, for our purposes, can be any server, anything that you really want. For simulation, we just had a laptop sitting beside our physical system that you'll see. This was coded in Python just because it's easy to do socket programming in Python. It's very quick, easy to mock up. And then also on the micro, we have a client that accepts the signal, processing steps. Now, the laptop, we have the graphic interface for modifying not only our, and also modify our resistance in the system. And that is from, if you looked at the difference equation beforehand, that our serial that we could manipulate inside the system, we can change that on the fly. The reason we want to do that is, again, as the system. So in analog, whereas you could change the inductance and the resistance and all that stuff with resistors and inductors, now we change both of these in order to stabilize the system. It is also possible to, just for impedance matching purposes, generate a inherently unstable system with our system to balance out any sort of poles or zeros that may exist inside a physical system that you what's going on in the background. You saw the front end of there where people could change the values, see what the values are. Values that we simplified our difference equation to represent. One being the inductance, one being the resistance. These are printed out onto the terminal to the end user, as you just saw beforehand, and in the final system, but just we're building a proof of concept, you could see that we have switch 2 system keyed in to whereas want to unknowingly to by some error inject some sort of catastrophic signal into the system. So we just have that actually as a buffer right now. But that can easily be taken out on the end user's point so they don't have to physically touch a button on the system each time to update their values. Now, as I said, we have an FRDM K64F board. This was chosen under advisement of Dr. Weldon and Dr. Conrad, mainly for its ARM core architecture because it's very, very quick. Has a whole bunch of floating point units, very, very fast. It actually has the DSP chip natively on board, and the DAC and the ADC are relatively good size for what we want. And even if we didn't want to go through an Internet of Things interface for this, it is provided with a Ethernet port on top of it. So this experiment. What we have is we performed 2 experiments after we did our validations of what we thought would be good representations of the system. So we kept the RDAC that was in the non-Foster circuit at a constant 1 kilo ohm. The RS right here is injected by the power supply, so that is a constant 50 ohms. We have that. We have these be a lot easier to compare with each other to find the character. We kept the serial resistance to -100 ohms for both of them. these two, the negative 20 millihenries and the negative 40 millihenries, to show that changing the resistance, is all well and good, but we wanted to change the inductance on it because that's really the new model of the system that we want. So the results analysis for the first one, the 20 millihenries inductor. This looks very, very similar to the simulation results. But as you can see here now, whenever we have a positive voltage, we have a negative current. So the slope is negative. This automatically tells us that we have a negative inductor into the system. So the real and imaginary part are reflected as such. Then what we did, doubled the negative inductance. As you can see, slope changed. The signal actually got a little bit smaller due to the gain characteristics of some of the system, but the current is still negative whenever the voltage is positive, which again, really, really want inside the system. So just to show these side by side now, again, you're at the point. Negative voltage, positive slope, positive voltage, negative slope. System that can be put in line with any sort of a stable system, or if the system is unstable, we can drive it to stability, which is probably one of the key aspects towards. If anybody has any questions, I'll accept any now.